All right. When we got back last week, we talked about the final project where we'll be designing and testing trusses. And I found an app that I would recommend for you. It's available for free. It's called Trust Me.
Like a phone app?
You can certainly download it on your phone. But what you might want to do is look at getting an emulator for your computer. If you're not familiar with what an emulator is, it's something that you can download, and it essentially runs just like a phone would and allows you to run apps. I'll post some directions. I won't get to it until tomorrow because I got to catch up from being gone the last couple days. But I'm running it on an emulator called BlueStacks on my computer, and it works real slick. So, and it just runs you through. The first portion is what's called challenges, so they're built-in systems, and so they'll give you things like a pin and a roller support, and you with some weight, and you need to figure out how to keep that weight suspended without the roller moving all over the place. But I think that will be a beneficial tool for you later this semester when we start looking at designing those trusses, so you can get a little familiar with it until then. And then you can, once you work through the challenges that they have, you can do there's an option called freestyle where you can set up whatever it is that you want, set up different nodes, and you can change the size of the members, you can add nodes to break things up, so it's a pretty cool little software package on there. So
Here's $1.99.
Yeah. It's not free.
what's that?
It's not free.
$1.99.
It is? Really?
That's the same one?
Yeah, that's the same one.
No. Do you have Android maybe?
Yeah, so I run it. Yeah, so I run on
Blast.
Well, I'll take a look around and see if there's anything else that's free for Mac users.
So for the emulator.
Well, and actually, well, if you get BlueStacks on your computer, BlueStacks is an Android emulator.
Oh,
So-
you don't. So it doesn't have to emulate your own phone.
No, you don't tie it to your phone at all. It runs completely separately. So yeah, BlueStacks. I'll get some directions up for you guys tomorrow.
All right.
So outside of that, I had a couple students out with me at the ACI convention over the weekend. So American Concrete Institute. There was a little bit of business that I had to attend to pertaining to shotcrete. I won't bore you to tears with that because that was not an exciting meeting, but dealing with how we prescribe aggregate gradations, and it got to be a fairly boring conversation. But I did see on Sunday a series of presentations on high strength concrete, and one of the really fascinating portions was on the Jeddah Tower. Is anyone familiar with Jeddah Tower? Doesn't have anything to do with Episode 8 of Star Wars, if you're thinking of the Holy City. But it's going to, once it's completed, it will be the first vertical structure in the world that's 1 kilometer tall. So it'll be the next tallest building. It's in the city of Jeddah in Saudi Arabia, so it's being built with oil prince money.
I heard about that.
They're about 260 meters along, and they started the project in 2014. So it's
been a hike.
It's pretty intense. So some of the things.
Keep importing that Australian sand.
What's that?
You're gonna use Australian sand.
Yeah,
It's
exactly.
Hilarious.
Yeah.
What?
They can't use the sand in Saudi Arabia or the Middle East.
Oh.
Fix concrete.
Yep.
So they gotta import it.
So everything's going to be imported.
Which is
So-
hilarious in the desert.
Probably the best use of money to be doing this project.
A man full of sand.
Do you know how much that project is?
I don't. I traded business cards with the presenter. So the presenter works for the design firm for the project. So should have the presentation hopefully in the next 2 weeks to look through, because it's pretty impressive. When they were pouring the foundation elements, they had 6 pump trucks going continuously. And they did a continuous 5 meter thick placement with these pump trucks.
Of this building?
I know there's.
What's that?
Are there renderings of this building?
I'm sure there are if you go online.
For what?
Jeddah Tower. I'm fairly certain it's JEDDHA,
Yeah, it is.
if I remember
Oh,
correctly.
it's like a,
I think I wrote that down from his
one of
slides.
those options that always comes up.
So, and if you're interested, the design program that they used is called Midas Gen. So Midas, just like King Midas of lower, and then gen, like if you're shortening generation. I don't know a whole lot about the design software. So it's transmitting load through 270 board friction piles. So they got a lot going on, but.
What is the function of the building?
To be the tallest building.
Just for funsies.
That's, I imagine it's gonna be mixed use, commercial, there'll be some residential, I'm sure, in there as well,
They're
so.
beating the one in
World Trade Center.
Abu Dhabi,
Yep.
and then the one in Abu Dhabi was like, we'll just extend a pole 600 feet higher.
Oh, is that
Yeah,
what
so
you're
they
gonna do
can
about it?
make it there at the
Sure.
highest and
Yeah,
kissing contest.
but I was surprised, so it sounds like Sears Tower is still holding its own as one of the tallest in the world, so pretty impressive for how old the technology was to build that building.
What was it, 1920s?
Yeah, teens or 20s, I mean, that thing's been around a long time.
Bet you people in Dubai are gonna come right back at that Jeddah Tower.
Yeah, it's gonna be,
They're gonna be
between,
fast, dude.
yeah,
It's just gonna be back and forth now.
yep.
That's literally gonna be like double the size of the Trade Center. That's crazy.
Yeah, it's huge. It's huge. So, so it's reinforced concrete, but they don't have any columns whatsoever. They're just using shear walls. And if you'll see, if you pulled up the design of it, all it does is it just angles in the entire way. Okay, so they have vertical shear walls, and the shear walls keep moving in, and just as these angled portions of the walls, as they come into contact with the shear wall, they drop off. So everything's built around the core, and it's standing on 3 legs around that core.
At 1,000 meters in the air, like obviously the wind
Yep,
is gonna be a lot different than on like ground level.
correct.
So like, how do they?
So
Like, is there just gonna be like a certain amount of tolerance for like?
Well, the base
flex?
is so huge.
I
because it
know, but
does
like at the top
the
though, it's still
TPFS.
gonna like.
Oh, yeah.
it's still gonna flex. Yeah,
It's-
the building will always be deflecting horizontally.
Right.
Now, we have to think about, ideally, people are gonna be occupying those spaces, right? And you don't want them to have to be taking Dramamine 24 hours a day
Right.
in order to occupy those spaces. So there are some methods that they can use. He ran out of time and wasn't able to get into all that, but as Rush said, right, we have massive structures at the bottom, massive portions of the structure to help with that stiffness. We have to keep in mind, what does it mean for concrete? Does concrete like being put into tension as it's being moved? So they had to really tightly control that modulus elasticity. And so a lot of testing went into it. They did just use, if you remember when I put up that 57,000 times the square root of F prime C, that's how they did their calculation to determine what they needed for their modulus elasticity. Then they did extensive testing. So, but everything is being placed as self-consolidating. So lots of high-range water reducing material going into it. So, so that was a pretty cool presentation.
How deep does their substructure go?
115 meters.
They're building on this.
115 meters.
Yeah,
Yep.
initially planned to be a mile high. The geology wasn't suitable.
377
Yeah.
feet.
It's only
Okay, wow.
only a kilometer.
That's a.
Pretty,
No, there
pretty
was,
deep.
Japan was gonna build one, I think that was over a mile, and it was gonna fit like 33 million people in this building. Like the base structure, it would've been taller than Mount Fuji.
Yep.
And then when they got down to the bees knees, they're like, what's the purpose?
Sure.
You know what I mean? It's like
Right.
it serves no
It's only
purpose
a
Yep.
mile and a half.
Yep.
than just to do it.
Just saying, you got it.
Yeah, so they ended up bailing on it.
Absolutely.
It would've been a city
Yep.
in a building.
Yep.
You just gotta sit there
Yep.
and count
Exactly.
before you die.
So,
Actually, 35. I figured
and then-
it'd round up.
hey, hold on. One other thing, so after that presentation, there was a gentleman who presented on, the whole purpose of this presentation was on high-strength concrete. And if you ultimately go into where you're doing residential construction, you're probably not gonna deal with high-strength concrete in your lifetime. It's not something that we need for residential construction. However, if you find yourself working in the commercial or industrial sector, I guarantee you'll be dealing with high-strength concrete pretty much on a daily basis. Okay, and you'll probably get to the point where you'll deal with ultra high performance concrete at some point, where you're dealing with concrete of 22,000 PSI or greater. But that being said, the high strength concrete is certainly something of interest. And so we had a very good conversation about it. I'm not the smartest person in the room whenever I go to these conventions, so I try to find the smartest person in the room and sit next to them. So I was fortunate to sit next to Dr. Charles Nemai from BASF, who was a former client of mine, and he holds a PhD and is smarter than all of us. I mean, if all of us studied concrete together for the rest of our lives, he's smarter than all of us will ever
PhD
be.
in what, structural engineering or what?
What's that?
What, PhD in what?
So he is materials. So he's a materials guy. So he oversees, so all the chemical admixtures that I get that we use when we make concrete in here come from BASF. I have an extensive network of connections with them. So before any of their chemical admixtures or their fibers or anything that they produce comes on the market, it has to get across his desk. And so after they presented on the Jetta Tower, there was a gentleman who presented on the difficulty of looking at cylinder strength versus core strength. So now, are any of you familiar enough, have you been on a job where you have issues with concrete, where you have to have somebody come out and core? Familiar with what it is?
Yeah,
Okay.
I have a job doing it right now where Brian Intertech's doing some test samples for me.
Okay, okay. So what the issue is, what's the purpose of the cylinders? What do the cylinders do for us?
I don't know, right now it's, for us, it was water that came through, so it's
Okay. Oh, okay. So you're more interested in,
moisture.
are there any effects to the concrete after it got placed, moisture was put into place?
Yeah.
Yep, okay.
They give you like a real life example of what the batch of concrete can withstand, hold.
Say that again, Justin, sorry.
Like they give you like a real life example of like the batch of concrete, like a real life example from your current surroundings and all that, like on job site. So it's gonna be the same. You can test that the same as the concrete that's already on your job site type.
So,
I don't know how to explain
That
that.
would
I
clear
thi-
that environment.
so what I think you're trying to say, and I don't mean to be rude about it. You're trying to say that you're using it to compare new concrete coming onto site against other concrete that's been placed?
No, my thought was like if you have concrete coming on into the site
Yep.
and you pour it, cures, you can take a sample of that, just make sure you're meeting like your requirements for,
The project requirements, right? Yep, exactly. So the whole purpose of casting cylinders is quality control. Okay. Well, that's all right. That's why we're here. That's why we're talking about it, to make sure we're on the same page. So the purpose of casting cylinders is not to say the concrete, I mean, this is a brick wall, but if this was a concrete wall, it's not going to tell us what the strength is of that wall, right? Okay? What it's going to tell us is when the ready mix producer bids the job and they're told your F prime C is 4,500 PSI. They test their mix, and if it tests out, and how they test it is just like what we do in here. When we're using the mixer, it's in a lab, right? They aren't going out in the field. They're not casting it at 80 degrees and then casting it at 40 degrees. They're not casting it in the rain. It's in a lab with controlled conditions, okay? So they cast those cylinders. They control its exposure to moisture. They control its exposure to heat. Okay, so we minimize temperature fluctuations. We keep them wet, right? Now, that sounds exactly like all project sites, doesn't it?
No.
Nice controlled temperatures, nice controlled moisture. Okay, so all we're interested in doing here is when we cast these cylinders, how do they compare to the test strength? Okay, does that make sense? Kind of?
So you're talking about like the test strength that was like done in the lab or out?
Correct.
So then the casting cylinders though are out in the field, correct?
So we can do field cures and we can do lab cured cylinders.
Why wouldn't the whole point of it would be to do a field cure?
Not necessarily, because what we want to see is we're not interested in trying to determine what the strength of the members are in the structure. Think about how big a cylinder is. There's gotta be one in here somewhere.
It's like a
Oh,
foot.
there's one
It's like
over
this
there.
big. It's-
Yeah.
It's a poor one,
It's crushed.
Yeah, we've already tested this. It's okay though, because it's got fibers in it, so it's gonna hold together. So typically speaking, we're not making 6-inch by 12-inch cylinders anymore. We're making 4-inch in diameter by 8-inch in length cylinders, okay? Now think about the concrete that's out on the job site. Are they similar at all in size?
No.
Not even close, right? Okay, so what happens to concrete as it's curing? What does it start doing? It starts increasing in heat. Okay, as it increases in heat, it increases the rate that the cement hydrates, so it drives the strength gain. Okay, so if our little itty bitty cylinders that we need to be at 4,500 PSI or at 5,000 PSI, our structural members are going to be 6,000, 6,500, 7,000, something like that, okay? So, we're not interested in trying to compare them. In comparing to structures, okay? We instead check the baseline of the mix. And so we're interested in things like, is the ready mix producer messing with the powders that's going in? Are they cutting back on the cement? Are they adding too much water? Are the moisture on the rock not correct?
So
Are they not using the right rock?
if that's done, let's say you're doing that not in the field, right? You're doing it, you went to Semstone.
So
How many trucks would that
So
potentially carry?
we never test at the plant. We always want to test at as close as we can to the place of the structure. Okay, so
So you do wait till it comes out?
yep,
Okay.
yep. So they're cast in the field,
Okay.
and then what the ASTM practice says is those cylinders can stay in the field for 24 to 48 hours. At that point, you got to get them back to the lab. Okay? We need to minimize the amount of temperature fluctuation that they're experiencing. Further, we need to limit the range of temperatures out in the field. We need to have a cooler, we need to have some sort of heating facility for them in the wintertime so that they aren't having the same temperature fluctuations exerted on them.
So if you did that out in the field, would be like, okay, these 6 trucks all got the same batch, or do you gotta do it per load?
So that's going to depend on your project. I was overhearing a gentleman talking about shotcrete placement yesterday where they test every truck. And that sounds absolutely awful. That's just going to completely bog down your day. What I would recommend is I would probably check the first 3 trucks of the day.
Because wouldn't it matter how
After
much
that-
that driver sprayed his hose in there, you know, if you got it too wet or anything like
Yeah,
that?
but
You know what I mean?
but usually the drivers, well,
I've had a
hopefully,
whole bunch of different mixtures.
hopefully the drivers aren't doing too much of that,
Okay.
right?
Well, because like depending on the time of day, can that affect it as well? Such
The
as
heat.
like if there's
Absolutely.
traffic longer
Yep.
or the sun's out more or something.
Travel
like that.
time,
Right.
yep, the sun beating down on that drum as it's driving to the job site, absolutely.
Or
So-
winter.
So how would you like? Do you think that they like account for that in their mixture before they load it on the truck?
They typically would. Yep, they typically would. So what you'll probably see is that your mix will have, so when I always designed mix at Braun, we always had chemical admixtures in it, right? But we have to keep in mind that I was working in a lab where I controlled the temperature from 70 to 77 degrees. And I kept the humidity between 50 and 70%. That is not at all indicative of what is going to go on in the real world. So the last item on my mix design submittal is specifications. Dosage rates of admixtures may need to change. And so one of the things that we can do on that is if we know that it's going to take us 20 more minutes to get to the job site and it's 90 degrees outside and it's sunny and that sun is baking down on that thing, burn it with a little bit more water reducer, right? If we're only using 3 ounces per hundredweight before, bump that up to 4 or 5 to help keep that mix nice and fluid for a while longer.
So if you add more water, like say if you did like an air and train mixture,
Yep.
and you added more water, would you have to adjust the amount of air and train that you put into it?
If you add more water, yeah, you would probably have to add air and
Training
training.
that would be more like diluted.
Yep. I would caution against recommending to add more water. Because adding more water is going to decrease your water cement
So
ratio.
what would you do then?
So I would try to, when you're doing projects like these, and most of the ready mix producers, I shouldn't say most, all of the ready mix producers in the Twin Cities are savvy enough that they're using some sort of water reducing admixture. So that will get you your workability without altering that water to cement ratio. So,
Yeah,
and
'cause I swear, like, we would pour, and this isn't big, you know, what I mean, we're doing people's patios. You know,
Right.
we're like, oh, make it wetter, because we couldn't finish it, you know, the
Sure.
aggregate was sitting on top, so we're like, slurry it up, and
Yep.
I would just, you know, we already signed for the paper, the mixture, you know what I mean?
Yep.
He's just going to town until we say when.
yep, well, and let's keep in mind the point of the application, right?
Yeah, it's
If-
not like structural.
If we're talking about patio block, you know, paver sections, if we're talking about footings for a deck, burning a little bit more water doesn't concern me, okay? But if we're talking about doing foundation elements for a 50-story tower,
Yeah,
we better not be, we better not be seeing any water going into that truck on the job site without it being documented to make sure that we aren't exceeding that. That we have to control that with our admixtures. So, yeah, being mindful of our application.
so is that stuff, like the retarder you put at the, after you finish it and you spray with that white stuff, isn't that what that is?
No, not a curing compound.
Okay.
Not a curing compound. So Rush is asking about curing compound. So a chemical that you apply to the top of the surface. It has a certain amount of particles suspended in water. So it sets in on the top surface of that water, closes all the pores, and then the water that it's suspended in evaporates. And so it blocks all that pore structure, so further water can't get out. We have to be careful with curing compounds to wait and put it on after the bleed water goes, right? Because if we block in that bleed water, all that happens is we're just gonna strip away that top layer of mortar, so. No, so these are admixtures that get added at the plant
Okay.
into the concrete itself, and they'll have it on the ready mix truck. So you can always tell the driver to add a little bit more. I mean, you can always have them
Oh,
splash it
okay.
down with
They'll
water.
burn it.
You can always tell them, burn it with a little more water reducing, okay? So, that being said, there are going to be times where we have issues with this material in the field. Logan's talking about a specific instance where they had a moisture event after placing. So, I imagine that the first thing that they're gonna do is they're gonna test the course for compressive strength, and then they're probably gonna cut a section, polish it up, and look at it under the microscope to see, do we have any breakdown of the mortar matrix right at that top surface. So a couple different things that you need to be aware of with that. If your compressive strength comes back fine, structural engineer might sign off on it, may not need to look at it. I personally would have it looked at under the microscope just to make sure they don't have a lot of breakup, a lot of localized high water content at the top of that concrete. But when we're doing the regular testing of our cylinders, there will be times where we may have a cylinder not meet strength, okay? And then we have to go into ACI 318, which is the code, says, okay, we've got to go in core. And this is why we're looking at placement of steel and depth of beams, so that we can have a little bit more conversation about coring. If we have to go in core, all we have to do with coring is meet 85% of F prime C with no core dropping below 75% of F prime C, so our design strength. And the reason you have that allowance is, first of all, it's in the design, right? But then second of all, we have to recognize that as we start cutting into that concrete with our core barrel, we're going to start fracturing some aggregate, we're going to start fracturing some of that hardened concrete matrix, so it's going to break at a lower strength, okay? So, we also have to be careful when we're coring. This gentleman who was talking about the difficulties with testing high-strength concrete, what they did was they did a big study where for a bunch of projects they cast these thermal boxes. So we're oftentimes interested in modeling what's going on with the concrete, how much it heats up over the time of placement. So they went and cored into these boxes. The problem was the box was cast like this. Okay, so the concrete was filled in this direction. They cored a section out of here. Okay? As you look at that, your initial reaction shouldn't make a difference, right? It's concrete.
Is that layers that they put in, those lines?
I'm just simulating
Oh,
that
okay.
the first portion filled up that, then
Okay.
they're, so, I don't remember what the dimensions of them are. If they were 8 feet by 8 feet, I mean, it's probably just coming out of a truck, out of one truck. They probably don't need multiple trucks. The problem with this is when we test cylinders in compression, but we also test them the way that they were cast. Okay? So we apply it in such a way so that we're compressing on the top surface. If we then core, but we core horizontally, now we're getting after different aspects of the mix that could take it into
So
account.
you just fill your core back up with more concrete? I mean,
Yeah, or you could do a patch mix, or yep. But you have to keep in mind these were just blocks that they had on site.
but
They
when
weren't
you're
using
talking
them
about
for anything.
typically about coring, you're talking about taking something out of the project.
Yep. Yep. So yeah, it's typically just some sort of patch that gets put in. If you go out and core a roadway, usually it's just the asphalt patch is what goes back into it. So, but yeah, you can put in a high strength, high early grout into place, so it'll have a higher strength component and it'll cure really fast. Okay. So, a little bit of sidebar that I wanted you to be aware of. We'll come back and talk about coring once we get through all the reinforcing steel, but it was a portion of the presentation that kind of bothered me because he came to some conclusions that I don't think were necessarily completely valid. And Charles felt the same way, which always makes me feel better when I'm sitting by somebody who's smarter than I am, and I'm thinking something and I say it to him, he goes, no, I completely agree with you. Like, oh, thank goodness. Okay.
So I have a question.
Yeah.
So when you run those cores, they're sure that doesn't make the strength decrease, or because it's agitated with them coring it out, that doesn't make the strength of that core less than if it was in a cylinder. You know what I'm saying? Because there's
Oh, no.
agitation. And
We definitely understand that it will be different then.
Is that why you go for that 85%?
Yep, that's why that 85% is allowed. Yep, with no single cylinder being less than 75%. Yep, no, that's a very good observation that we have to be aware of, that they are not going to be the same strength because they're not treated the same, right? The one thing that the guy did get right is he kept referring to cylinders as unicorns, in that they're really cool, they can tell us a lot of information, but they don't truly represent what's going on. You know, it's not a good representation of what's going on with the concrete. So, oh, and then Marshall, you'd asked about field cures. Field cures are something else that you can do. Just be careful with them. Field cures, really the only good value for them is when can we pull forms, when can we pull insulation or heating. That's really all that it's going to tell you. From the standpoint of what's going on structurally, tensioning, things like that, things of that nature, do not use field cures for that, especially not for tensioning. Okay, so you'll get away with it most of the time, but at some point you won't get away with using a field cure for tensioning, and you'll bust a tendon, and no one will be happy on that. So. So we left off, we were looking at a beam that had 58 kip feet for dead bending and 38 kip feet for live bending, right?
Correct.
And we also have that F prime C is 3,000 PSI. And F sub Y, our steel strength is 60 KSI, right? And we need to determine our beam depth.
We also had that it was, the width was 10 inches.
And our tensile reinforcement. That's correct, thank you. Okay, and we left off with, we determined little d, right? We figured out that we needed essentially 3¼ cubic inches of steel, right? And that our depth needed to be 12.8 inches.
Yep.
Okay.
Yeah. So little d was the square root of mt over dr.
Yes.
What was AS?
3.23.
Yep.
Oh, what does it mean? AS is the area of steel,
Oh, yeah.
right? So remember that A sub S is the total area of reinforcing steel that you need in your tension face, okay? So now we can start constructing this thing, right? Because we know that this distance is little d, right? I forget, did we cover, did I give you a common value for stirrup thickness when we talked?
0.592.
The percent of steel?
No. So when we construct our beam, so we're going to look along its axis. Okay? So our beam's coming out of the wall towards us. It's going into green 39. We'll have our stirrups to support. Did we talk about a thickness for this?
No.
Okay. So we will assume our stirrup thickness will always be 3/8 of an inch. Okay, so 0.375 inches, just to make our calculations easier. Okay, in the real world, we'll sometimes use different thicknesses depending on what type of reinforcing we're putting in. But for the purposes of our class, this is all we're going to use. Okay. So we'll need to figure out, because we know what our width is, right? But now we need to know what our total beam depth is, right? Because remember that this 12.8 inches, all that tells us is the distance from the top of the beam to the center of the reinforcing steel, right? We need to take into account the other half of the steel. We need to take into account the thickness of the stirrup, and then we need to take into account the cover of the concrete. Okay?
I have a quick question.
Yep.
In this example, where we got 12.8, is it like a slab,
This is a beam.
a beam?
Yep.
Why you only have the one reinforcing steel, you don't have like one towards the top?
This would likely have reinforcing steel at the top, yeah.
Why are you taking the distance from the bottom one? You don't have
Because
to put anything else in the
this
top?
steel that we're determining is steel for the tensile compression. Okay? What John is asking about is oftentimes in beams, there's going to be steel at the bottom, there's also steel at the top. So the first step is determining how much steel in your tensile face. Once we get through that, I don't think that we're going to have time to look at calculating and determining the amount of steel that we put in the compression face. Okay? But it is something to be aware of. But yeah, the steel in the compression face is not a portion of this determination, because remember, what we're attempting to do is balance out the force that's shearing and compression on this beam with tensile force, so that as they try to rotate each other, they balance out and don't spin the beam out, okay? That's a very good question. It's a very good question. So when we solve for our beam depth, how do we need to set it up? What items are we gonna put in? We need D, right?
D.
Plus your 0.375.
We're gonna need the thickness of our stirrups. What else are we going to need? We're 2 items away.
But you need to figure out the other half AS by, so if AS is 3,
Careful, what is AS representing?
the total area
That's the
on
total
your
area,
cross section.
right?
So you need to figure out
We need to figure out the other half of,
the area.
yep. So we need half of our bar diameter. Right? Absolutely. And what's the last item that we need? Do we need to protect the
wouldn't
steel from the environment?
Aren't we just looking at one face of that? So wouldn't we take the bar diameter and try to figure out 1 and divide it in half? Because that's all 3. Your AS is
Yes.
3.
Yep.
So you'd want to put it down into 1 and then take half of that.
Yep.
So once you take AS divided by 3, divide by 2.
I wouldn't do that, because remember that AS is giving you this information, right?
Mm-hmm. So if you divide by 3, you just look at the 1, and then divide that by 2, and you got that other half too. So we're
But
just
if you
looking at
take-
the side
but if you
view.
It'll
take-
give you the area of it, won't give you the height of it.
Yep.
Okay.
Does that make sense?
Yeah.
I see what you're getting at. So if we take AS and divide it by 3, that reduces it from that to that,
Mhm.
right? If we take half of this, we will be left with that, right?
Mhm.
But what do we want? We want to know the linear distance from the middle of the beam to the bottom face of the beam. Okay, so, and we certainly could to figure it out that way.
Yeah, I see. It's just more work.
Yep,
Yeah.
it's more calculations, because you'd have to
Okay.
take the surface area of the bar that you'd want to use, you have to divide it by pi, and then it's giving you, or no, sorry, you'd have to take your area, move it over into circumference, divide by pi, and then you'd have your
Yeah.
diameter. So you could certainly do it this way. It would be a bit more challenging for you, okay? If we so we have to be aware of this condition, but if we instead look at it this way, it makes it a little bit easier, okay? So we have little d. We've taken into account the other half of the bar diameter. We've taken into account the thickness of the stirrup, right, that's running up.
You need to look at the thickness of the concrete.
We need to look at our cover of our concrete over the top of it, right? And remember that we said for beams, we're going to do 1.5 inches. And for walls and columns, we're going to do 3/4 of an inch. And again, don't fall into the trap of this is what we do all the time in industry. It's not the case all the time. Generally speaking, if we're doing basic, straightforward concrete design, 1.5 and 3/4 inch will be sufficient. But if we start talking about massive members, if we start talking about really high strength concrete, we might have to start providing more cover, okay, to help support that weight. So there's really no guideline for us in figuring out this bar diameter, okay? So it's just going to be an iterative process. We have to throw something in there to start and figure out what's going on, okay? So we know that D is 12.8. And we'll say that we're just gonna look at a bar diameter of 1 inch, okay? It'll make our lives easier. And we're dealing with a beam, so we need 1.5 inches for cover. Okay? So what does that calculate out to for everybody?
15.175.
15.175 inches. Okay? So now that's telling us that this distance is going to be our 15.175. The last item we need to look at is check and see, okay, now if we put in this 1 inch bar, is that going to fit into our beam that is 10 inches wide? Right? Because what is our beam width going to look like?
You're gonna have 1.5 on the side. Each side.
On each side, right?
Yep.
Yep. So we need
7 inches.
2 times our cover. What about the stirrups?
Stirrups is 2 times the,
We're gonna need 2 times our stirrups, right? What else are we gonna need?
3 times your 1 inch.
We're gonna need our beam width, and we're gonna need our beam spacing, right?
so that's gotta be,
Or, sorry,
The 1 point-
not beam width, I'm sorry. Our bar width
Yeah.
and our bar spacing. Okay, and bar spacing can get fairly complicated. We will look at very simple applications where we're just going to, we'll figure out their widths, we'll figure out how many of them we're going to need, and then we're just going to evenly space them for the purposes of this class, okay? In the real world, we have to take a look at things like what's the largest aggregate that we're using, how much space do we need to keep them off the wall, things of that nature. So we're gonna really simplify things so that we can actually get through this, okay? So if we looked at a number of,
so that 1.5 for the cover,
1.5 for cover, yep.
that's only on the outside. Right.
Outside.
So that's, you need 1.5 inches on each side,
We need,
not in between each one.
That's not.
correct,
That's not the spacing, okay.
correct. We need 1.5 inches
For, I don't know where you got.
right? Okay, and so everything's drawn perfectly to scale, so they're all an inch and a half in distance, right?
Yeah, it might have been 13 points.
So if you turn to, it's 13.2, right, that has diameters and areas of the different steel bars, right?
That's 13.
Oh, no, that's not
You
it.
want 13.1.
13, the 13.1 that has the,
It's like 460 or something.
Yep. Okay, so by 13.1, we can take a look, and all we need to do is we need to determine the different bars that are available to us. How many bars are we going to have to put in? Okay, so What if we use number 6 steel? Number 6, so we have AS,
You need to use number 8.
the total area of the steel, divided by area of the bar, right? So 3.23 inches squared divided by 0.4 inches squared equals 7.3 inches. Does not equal 7.3 inches. It equals 7.3, right? So that tells us if we were going to put in number 6 bar, we would need 7.3 bars, okay? Or 8 bars, right? We're always going to have to round up. What's the diameter of number 6 bar? 3/8 of an inch.
On a number 6 bar, 3/4. 0.750 diameter.
Yep.
No, I get what you're saying. The number of a rebar is that an eighth. So
Yep. So, how much space are we going to need if we're putting in number 6 bar? How much space do we have? 3 plus 1.5, right? That's just our cover and our stirrups.
So you get 5.
So if we have a 10-inch beam, we've got 5.5 inches to work in here. Okay? Is 8 bars that are 3/4 of an inch in diameter going to fit? No, that's not going to be an option for us. Okay? So we can march all the way down, but let's look at number 8. Okay, so 8 is 3.23 inches squared divided by 1 square inch.
For our area of steel, where did we come up with that previously? Is that just something you threw out to us, or
No, no, no.
did that actually come from?
We calculated, remember that AS,
So it's 1.076 if it's 1.
what's that?
I'm trying to figure out where we got it from.
Remember that we're looking at an instance of bending, so we use the moment equation for it. So remember that moment of tension equaled,
You're talking about the AS times FY?
yep,
Okay.
AS times FY,
All right.
1 minus A over 2D.
It's a problem so long, it's taken over a week to do.
That's what happens with these sometimes. I saw both of the structural engineering professors from the U this weekend and talked with them, and I told them that this is where we were in class, and they had told me that now do they understand why they got so upset with me when I was a student in their class, and I was going through this, because I certainly struggled with this class when we went
Do
through
they
it.
remember you?
So the one woman I did not have, Professor Shield did remember me. And the one thing that she did remember is, because I was in her office all the time, she said, yes, I do remember you because you always did very well on your homeworks and then you always struggled very much on the exams. I said, yes, you did say that to me, I do remember that.
Imagine
So,
that.
Yep. So, you're not the only ones, I've been there, I know what it's like.
Shit, you're doing a little harder.
Okay, so, and then let's look at if we were going to do number 10 bar. Okay, so if we look at number 10 bar, I'm sorry, that should be squared so that we get rid of our,
So
It's right there. Look at number 10, diameter inches.
do we want to come up exactly with the 5, I mean, why wouldn't
we'll come
8 work?
exactly with the 5.5.
Because we have 5.5
Oh,
inches.
I see what you're saying.
But why wouldn't 8 work?
You didn't answer me. 6 times that.
So it's 3 point,
But remember,
No, that's 6.
this isn't telling us the distance, right?
What?
This is
Oh.
telling us the number of bars that we're going to need.
Okay.
okay? Because our units, we're doing inches squared divided by inches squared, so we have a unitless dimension. So it's just telling us the number of bars that we're going to need to meet that
Yeah,
area
so
of steel.
when you look at 8, you need 4 1-inch bars.
Yep,
Oh, so we can't even put like an inch. What if you put a 1/2 inch in between them? Is that, don't fly?
so if we're gonna put a 1/2 inch in between them, we have to place a mortar. We can't place concrete.
Okay, oh, because the aggregate. Yeah.
We're not gonna be able to get 3/8 inch aggregate
Yep,
through that.
okay,
So yeah, that's where the problem comes in.
all right.
Okay, so, yes, we could look at doing 4 number 8 bars, we could look at doing 3 number 10 bars, but what is the problem? What happens with this problem? We can't get to the point where
Buildable.
we're able to actually construct this thing, okay? And what your book does with this example is they say, easy, widen the beam. And I bet that works 100% of the time out in the field, doesn't it? We'll just make the beam wider. We're not gonna have any issues. Yeah, Terry.
For number 8, why did you use 1 inch square?
It's a 1-inch bar. Diameter.
What is it for?
In cross-sectional area, it's saying it's a 0.79. And we use the 0.44 for the other one, and you use 1.
0.79.
Yeah, you're right.
Oh my god.
Well, I've been trying to wrap my head around where he's getting these numbers.
Yeah, no, it's fine.
So,
Uh,
3.23 divided by.
yeah, I may have calculated that incorrectly, Terry. Thank you for pointing it out. So that's 0.5, so it becomes a quarter of pi.
So you'd be at 4.08.
0.25 pi. So yeah, that is less than 1. Yeah, it's gonna be, what does it say that it is? 0.79?
Yeah,
Yeah.
0.79.
Yep, that's reasonable.
That puts you up to 5 bars basically, so.
So that's gonna turn that into,
Or 4.08.
yeah, it's
Yeah.
gonna be just over 4,
Yeah, right.
right? So it makes it even less appealing. And that's, sometimes, Kurt, that is what has to happen. But if we want to stack the bars, what happens to our beam depth? Careful,
Oh,
You gotta increase it.
we gotta
it gets deeper.
we gotta make it deeper, right? Because the first thing that's going to happen if we make our beam depth deeper is we no longer have 1 layer of steel, we have 2 layers of steel, right? So if we're looking at it in cross section, our tensile force is going to move. That D minus A over 2 is going to move, right? And so it's going to result in needing a deeper beam, okay? So that's what we have to look at balancing is, can we make this thing wider? Or do we need to make it deeper and put in more bar?
You ever put
Okay.
one big bar here and then smaller ones, or that type of thing?
Typically speaking, they would like you to stay away from that. From a design perspective, it certainly makes sense. Constructability is where you're going to run into issues. You can do it. Iron workers are not going to like you, right? It's going to make it difficult for those guys to get everything placed. It's going to make your special inspections take a lot longer. So as a portion of the constructability is you have to have somebody come out and ICC certified inspector and look over these things. And so if we start having, 1 inch here and 3/4 inch and then 3/8 inch, it's just going to make it a nightmare out on the project. So it's certainly a good idea as a way to get around it.
It's like you're using your scrap pile.
That's how I'm gonna solve my
Yeah.
exam questions.
So if you do it where you're gonna stack them, is your D between the 2 white, the 2 steel lines? Because you know how you're going on the center of the.
Yes, that's a good question too. Is Steven's wondering how are we going to determine this? It's going to depend on how we actually lay it out, right? If how we actually lay it out is like this, where we have 2 bar in the top layer and 3 in the bottom bar,
I'm thinking.
It won't be halfway in between them. It'll be closer, it's gonna be closer to the layer where there's 3, because we're gonna have more mass down there.
So you take your mass and figure it out.
Yep, yep. Okay,
All right.
so, yeah.
I'm gonna have to go rewatch the first day.
Okay, so that's the portion of this type of problem, and I think it's kind of a bad first problem that they don't really come up with a solution. They just kind of get you to this point.
with this problem now?
No.
What's the answer?
There's none.
So we don't know enough about the conditions to take it further.
I thought I chose 14. Why can't I use that?
You chose what?
14, number 14.
Number 14?
Yeah, bar
What does
number
14 give you?
That's gonna be like
1.43.
1.43 inches?
No, that's just how many bars.
It needs to be-
Okay, so you need 2 bars.
Yep,
Okay? So 3.23,
yep, it's 2.25. No. 3.23 divided by 2.25
gotcha.
gives us 1.43.
I didn't take it that far out. Okay, so,
So with that, right, and you put it into there, problems solved.
it could work. Now, the problem that you might find with that is
Not so fast.
if we put this in,
Now you don't have to steal.
so we determined that this is what? So this is 1.5 and 0.375, so this becomes 1.875 inches.
So
Not
you push down your
18.75, right?
cover, this is what's happening.
And this is, what's the diameter, did you say?
1.7.
No, 14 is 1.69.
So, okay, so 1.7. So we have 3.5 inches that are reinforced on both sides.
But wouldn't you just move the bars in?
Why can't you use a smaller bar
In the middle.
You could look at using a smaller bar.
for the middle?
Oh, again,
We just talked about that.
yeah, I would not recommend doing that. The problem that you're gonna have, John, is
Vinny. We literally just got them
Yeah.
discussing this.
now you got iron workers who have to keep track of how they're placing this bar, and then you have a special inspector coming through afterwards, looking to make sure that we've got the correct diameter put in place. So, it's certainly something that we can do, it's just going to slow down your construction schedule.
Would you
And
want to
make
do
people
that?
hate
I thought you
It's
just
gonna-
needed 1.5 inches from the bar to the end of the cover. So why do you have 3.5? I get you're using, hey, well, how big the bar is, but
That's my distance to here.
that's where the 1.5 needs to be?
No.
3.
No, 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 no,
It's
no.
3.5
No, 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 no.
wide
This
because
is
the thickness of
Oh.
the
I'm taking an inch and a half of cover,
bar.
Sure.
the
And-
thickness of our stirrup,
Okay,
and the diameter of the bar,
okay,
That
right?
equals 3.5.
So that gets us, I mean, yeah, roughly 3.5 inches in,
Sure.
right?
so we're
We
7
have
inches
3.5
all in,
inches over here,
and put 3 inches of space in there.
okay? Now we have 3 inches of unreinforced concrete. What's going to happen when we load this beam?
It's gonna crack.
Well, the
right?
strength of the 2 bars, that's all that's needed, we'll hold it.
We have to be careful, we have to be careful. It meets the area of steel requirement,
Okay.
okay?
Ain't that what this whole deal was trying to,
It doesn't mean
this
the
one needed, this
tensile
one,
Yep, yeah, so
requirement.
we met the math,
okay.
right? We met the math. We also have to meet the craftsmanship where we figured the art
Yeah,
of
you
it to make sure that we aren't getting into a section of too much unreinforced concrete.
So would we take that information we got for bar 14 and see if it meets up with your F prime C or F Y or anything, or how do you?
Well, we know that it will, right? Because we determined AS off of that.
So from there, then we can just say, you know what, they won't build it this way, it's no good.
Correct.
Pretty much then.
Correct. So for this particular project, what it is this gets rejected and they say, okay, you have to reiterate this thing. Either you need a wider beam or you need a deeper beam, okay?
Okay.